Welcome back to the Maintenance Factory. In today's video, we're going to talk about how a step-down control transformer works, and we're going to take one apart. So stick around. So once again, welcome back to the channel. Today, we're going to spend a few minutes talking about the basic principle of operation for a step-down control transformer. I've got another video out about the basic principle of operation for a motor control circuit. Within that circuit is a real basic step-down control power transformer. I'm creating this video so that we can get a better understanding about how that individual component works. And later on in the video, we're actually going to take one of these things apart so we can see what it looks like on the inside. I'll leave a link to the video in the description below so that you can go check it out, as well as a couple of other videos. So let's talk about one of these examples I have. So here is a really small step-down transformer. It's got 4 terminals on the primary side, 4 terminals on the secondary side, as well as a nameplate with a small schematic that shows us how to terminate the primary side as well as terminate the secondary side. Now, traditionally speaking, when a transformer is oriented in this position with the text in the legible direction, the top side of the transformer is usually the primary side. The bottom side of the transformer is usually the secondary side. That's not always the case, but generally speaking, that's usually how they're mounted in the panel and how they're wired and configured. I've got another transformer here, which is the actual transformer that we will take apart later on in the video. And it is real similar, except it's just much larger. Again, it has 4 terminals on the primary side. It has 4 terminals on the secondary side. It also has some nameplate information as well as a schematic that tells us how to wire this thing up. These transformers, as well as many others, are built with segmented pieces of steel. We usually call those laminates. And this transformer has got an E-shaped core. So if you can imagine, this E shape represents one steel laminate. And to get the thickness of the transformer, you can imagine multiple laminates that are sandwiched together, stacked one on top of another, and then they are put in a press, pressed together, and then they are either riveted, bolted, or welded together to maintain this form or this shape. There's also another steel crossbar on the top, which again is also made of many lamination segments, and they're also welded here, 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 and here. These 4 weld points correlate to the 4 weld points on this larger transformer, and they serve really 2 purposes. The first is actually to hold the laminates together to keep those from separating and to provide some mechanical stability to the core. These top welds here actually serve the same purpose, but with the addition of maintaining the top crossbar in close relation or contact to the E-shaped core. Now, within this core, you have some insulating material, oftentimes, that lines the inside of the core. And this insulator is there to protect the coil windings from becoming in contact with the core itself. And sometimes this is the case, not always. And then the next thing we want to talk about is the actual coil windings themselves. So you have 2 major coils within this transformer, or at least in its most basic form. So you would have a primary coil, again, and then the secondary coil. Remember, the primary coil is usually oriented on the top side of the transformer, with the secondaries oriented on the bottom side. And there's also another key indicator to determine which is primary and which is secondary, and we'll talk about that later on in the video when we have this thing on the bench and we're getting ready to take it apart. So let's draw in the primary and the secondary coil now. So on the primary side, in our example, we're going to put several turns of wire here, and we'll label this the primary. And in today's example, we're going to draw a 4-to-1 ratio or 4-to-1 turns ratio transformer. What that means is, on the primary side, it has 4 times as many turns or revolutions of windings than it does on the secondary side. And that is how you wind up with the 4-to-1 step-down ratio. So on the primary side, for example, if we were to connect 480 volts of alternating current, and we'll also say that it's 60 hertz, more on that in a second. We'll say on the secondary side, we have, remember, less turns. There's a 4-to-1 turns ratio here, and this is the secondary side. On the secondary side, if we had 480 volts applied to the primary with a 4-to-1 turns ratio, that would give us 120 volts of alternating current on the secondary side. Now earlier I mentioned the frequency at which the input or supply voltage is that's attached to the primary, and that's important to note because on the secondary side you're going to get the same frequency on it as well. And also the voltage type. I think some people have a misconception that transformers step voltage down and different voltage types, but that's not the case. If you put alternating current at a known frequency on the primary side, you're going to get alternating current on the secondary side with the exact same frequency. So here we've got AC current on the primary, we'll have AC current on the secondary, 60 hertz as an input, it'll be 60 hertz as an output on the secondary. Again, the difference is it steps down the number or the amount of voltage between the primary and the secondary. And the way it does that is by the number of turns related to the primary and the secondary. So how does this actually transmit power between the primary and the secondary? Because you could actually draw a line or separate these two coils. Now they may not physically be separate in the construction type, but in theory you could completely separate these two coils as long as they're in close contact with one another and on the same core. Then it's still going to work, still going to serve the same purpose. So how this works is as voltage is applied to the primary side and current flows through the coil and the windings, there is an electromagnetic field that is then generated, and eddy currents begin to circulate through each individual lamination of this core. As these eddy currents swirl and flow through the laminates on the core, they induce current onto the secondary coil. So this works off a principle of electromagnetic field. The electromagnetic field generated by the primary side creates eddy currents in the core. These eddy currents in the core then induce voltage or current into the secondary side. So that's how you are able to get voltage that's on the secondary side. Again, they have to be in close proximity to one another. They need to be on the same core. But we'll see later on in the video that the construction type of that, it is true in the sense that they are very close together, but because these transformers have actually 2 primary coils and 2 secondary coils, their construction type is just a little bit more complex than what we've got drawn out on the board. But I drew it out in a simple format so that we can get the basic concept or the principle on how this thing operates. So let's go ahead and take this thing over to the bench and we'll give it a look over and we'll start to take it apart. So here we are with our transformer on the work table. This transformer is the larger of the 2 that I showed earlier, and we'll talk real quickly about some of the nameplate information. This is not a video on how to connect a transformer. I will put another video out a little bit later on about how to actually connect one. But anyway, they can be a little bit confusing at first if you've never seen one or never installed one. Different manufacturers lay these out in different ways. But more or less, let's concentrate on the terminals themselves. So this right here are the 4 terminals on the primary side, which would where you would connect your higher voltage level. Here are the 4 terminals that's on the secondary side, which would be the load side of the transformer or the devices that you wish to control. Normally speaking, you would have a lower voltage on the secondary versus the primary side. So as mentioned earlier, we would have 480 volts applied to these 2 terminals on the primary, and then we would get 120 volts output on these 2 terminals on the secondary. Now, getting back to the label here, you can see there's some numbers and letters. an X4, X2, 3, and a 1. You have an H1, H3, H2, and H4. These correspond to the terminal numbers on the primary and secondary respectively. So this X4 means that this is X4 terminal. X2 is X2 terminal, X3, X3 terminal, and so on and so forth. Same thing for the primary side. This is terminal H1, H3, H2, and H4. Now, if you were to look at this schematic drawing of the transformer, this is a little bit misleading. What this is showing you two different configurations of the same transformer. So if we were to just blank out one of these, you would see that you have a total of 4 coils. Remember, our drawing earlier only had 2. It had one primary coil and one secondary coil. Here we have a primary coil here, and then another primary coil here, with a total of 2 primary coils. The secondary side is the same thing. You have 2 individual coils on the secondary side. They do this so that you can generate multiple combinations of primary voltage related to the secondary voltage. So if you were to configure the transformer like this, where you would have a jumper between H3 and H2, and you were, say, connecting 480 volts of power to the primary, and then you were to put a jumper between X2 and X3, then that means you would get 240 volts on the secondary side, and that's still a 4-to-1 turns ratio relationship between primary and secondary. So again, I'll put out another video about how to actually terminate and connect a transformer. That's not today's topic. So we'll look at the construction type just a little bit before we take this thing apart. There's a couple of bolts here. These bolts just simply hold on this plastic rail or this plastic tab that holds the termination points. You can see on the termination points you have a soldered connection. It's probably silver soldered at each terminal point, and then you have some wires trailing off from it with some fiberglass sleeved insulation. There's also some insulation wrapped around the outside perimeter of the coil. There's insulation on the top side of the coil to protect it from the iron core. Again, this outer sleeve protects it from the iron core. There's a little bit of a gap here, but a little bit deeper into the transformer, there's not much gap at all. In fact, there's probably interference. And then on the bottom side of the coil, again, we have some more insulation on it to protect the windings from the core itself. The insulation also protects the coil windings from whatever environmental conditions this transformer may see. So it may be in a dirty, dusty environment or somewhat humid environment. It may have some dirt and debris, accidental strikes from a hammer or maybe from a screwdriver, and this insulation is just another layer of protection for the windings themselves. Again, we talked about the segmented laminations. Roll it on its side, you can probably get a better idea of what that looks like. So if you look at this and it looks like striations in the core of the transformer, that is actually individual segments of lamination that has been sandwiched together and then welded here and welded here. And the same's true on the opposite side. So let's go ahead and take care of these welds so we can remove this top bar, and I'll show you a little footage about that. And then we'll have to burn this thing out just a little bit so that we can remove the coil from the actual core itself. So let's get started taking it apart. So what I need to do to take this thing apart is grind this down until we get through the welded portion on both sides. And then after I do that, we should be able to take the top piece off of this transformer. All right, so here we are. We've done a little bit of damage to this thing. Let's see if we can figure out how to take the rest of it apart. I've not taken this apart yet, so this may take a second. I think the first thing I want to do is go ahead and cut away these terminations. Okay. And then we'll get us a wrench and unbolt this thing, this top bar. All right. Okay, now the connectors are off. May have to get a hammer. All right, let's see if this will work. Okay, now it's starting to separate. So these laminates will probably fall apart. I could probably break them open. So yeah, you can kind of tell that they're individually segmented pieces here. And it's pretty easy to take apart once you have a grinder a hold of it. So here we are back to the work table, and we have our Burnout Transformer, and these things really make a mess, if you can tell by all the little pieces, bits, and parts laying everywhere. But here's just worth noting the laminates of the core is starting to come apart because this thing's really losing its structure at this point. The core actually gets submerged in some type of a varnish or epoxy, and that varnish and epoxy just basically impregnates itself and coats this entire assembly, and it goes into an oven, become baked, and then once it bakes it becomes hardened, and that provides some more structural stability to the coil and also a little bit to the steel laminates as well. But the majority of the structure for the steel core is provided by the welds, and you've seen earlier where we had to grind those away so that we could remove the top bar that was on here. So anyway, it's just worth noting that this whole thing gets submerged in either a varnish or an epoxy. It gets baked, and that provides even more rigidity and structure to the assembly. Now that we have this burnt out, we can easily remove this coil, which I've already had it off once, and this thing's getting pretty fragile on me. And again, that's because it's losing all of its structural integrity. But if you would look right here, these wires here are of a larger gauge, which it's going to be hard to tell on the video, but these are of a larger gauge, and the other one is down here. It just broke out, so here it is. So these 4 wires here were terminated to those 4 terminating screws that we'd seen earlier. This right here is the secondary side. I know it's the secondary side because, well, for one, I took it apart, and for 2, this is a larger diameter wire, or a larger gauge wire. If we look on this end, this is these are the 4 wires here that was connected to the primary side, and I know it's the primary side because these are constructed out of a thinner gauge wire. So that is a real good key indicator on determining which side of the transformer is primary, which side is secondary. The primary side has a thinner gauge wire. The secondary side will have a heavier gauge wire. So we'll look at how this coil was actually constructed. And like I said, it's getting fragile, so it's quickly falling apart on me. But if we look at the innermost turns of the coil itself, they are constructed out of the thinner gauge wire. So that would tell me that one of the primary coils was wound around a mandrel first, and then they went back on top of that with the 4 coils of the or the 2 coils rather of the secondary side. So you have 1 coil in the middle that is primary, you have 2 more coils that are secondary, and then they layered on top of all of that with another thin gauge wire, which is the second coil for the primary side. So I hope this just gives you a little bit of an idea about how these things are actually constructed, kind of what they look like, the relationship between the primary and the secondary coil. If you got some value out of the video, give me a thumbs up, consider subscribing, click the notification bell, and then you'll be alerted to the next content we put out. Once again, thanks for stopping by.